Hello everyone and welcome to the presentation of acid pKa values. Acid pKa values are often presented on reference tables. I'm going to show you one of those on the next slide, but let's break this down first just so that it's not too overwhelming to start. The components of that acid pKa reference table consist of the compound with the specific proton that the pKa value is referencing highlighted usually with a certain color. I've chosen pink for my table and this small example table. So for this compound, this acid, the name of this compound is hydroiodic acid. Hydroiodic acid has a pKa value of -10. This value depicts the strength of the acid, and this value correlates with the most acidic proton represented on the table. pKa values range from -10 to 60. The lower the pKa value is, the more acidic the compound is. For acids, deprotonation of the acid always results in formation of its conjugate base. The strongest acids form the most stable conjugate bases. So hydroiodic acid is the strongest acid. This is going to form the most stable conjugate base. Let's show an example reaction of that. For the example reaction, we need a base to deprotonate our hydroiodic acid. Let's use sodium hydroxide, as that's a pretty common base. And I'll just draw the hydroxide anion to simplify that. So for the hydroxide anion, we have oxygen and hydrogen, 3 lone pairs on the oxygen. Since this oxygen has 7 electrons as a negative charge, we're going to use one of these lone pairs of electrons to take that proton. And the electrons holding this acidic proton are going to move to sit on what will be the conjugate base. So that means we have formed our products. And I'm going to wait and draw the arrow here because I want to talk about the equilibrium balance. But for our products, that means that iodine now has a negative charge. And we've added a proton to the oxygen. So that means now our oxygen has 2 hydrogens and 2 lone pairs, and we've formed water. So we have our base, our acid, our conjugate base, and our conjugate acid. Again, looking at point 3, the strongest acids form the most stable conjugate bases. So what we're saying is that iodine with the negative charge is an extremely stable conjugate base. In fact, you can't get much more stable than the iodide anion as a conjugate base, which means that the equilibrium balance will lie strongly in this direction. Our strong base and strong acid will definitely interact and pretty much fully form the conjugate base and very weak conjugate acid. All right, let's look at the second reaction. So with this, we have propane. So let's use the same base again. Let's use sodium hydroxide as our base. Deprotonating propane, these electrons are going to attack that hydrogen, and these electrons are going to go to the carbon. Looks like I forgot the negative charge there, so we'll draw that in too. And again, let's not draw the arrow yet, but let's go ahead and draw the conjugate base. So this carbon right here now has 2 hydrogens on it. 1 was taken. And we have a lone pair of electrons on this carbon, and we have a negative charge. So this is the conjugate base, and for our conjugate acid, we again have water. Now looking at this conjugate base, this is a very strong base, so this is about as unstable as you can get. Looking at the pKa values of the original acid that we used, we've got a pKa value of about 60, and with water, the pKa value, so our conjugate acid, water, our pKa value of that is about 15.7. So water is a much stronger acid than the original acid that we used. So that was our acid and that was our base, which means that equilibrium will lie toward the more stable of the 2 acids. So it's definitely going to favor the starting material side, and a very small amount of product will form. The reason I've drawn these is because often on the exam, you're going to be asked to essentially show whether or not the starting materials or products will be favored. Having an idea of the relative pKa values is important, and you're not always going to have that table showing the specific pKa values for reference, which specifically is why we're going to look at factors impacting the pKa and stability of the conjugate base so that you can know essentially which would form a more or less stable conjugate base relative to something else. So let's look at the first reaction again. That first reaction is related to atom electronegativity and size. So iodine is somewhat electronegative, not super electronegative, but the size of iodine is extremely large, meaning that that negative charge can be spread over a large area of space, which is what allows this to be so stable. So atomic size is the reason that hydroiodic acid is the most acidic acid, and its conjugate base, iodide, the iodide anion, is the most stable. Looking at how this relates as we continue, there's no resonance potential with this. There's no other place that negative charge can go. There aren't any inductive effects. There aren't any other functional groups on carbons away from where this iodine is. And in terms of the orbital, looking at iodine in comparison to chlorine or fluorine or bromine, all of those electrons would go to the same orbital, so that also has minimal impact on how stable the conjugate base is. So that's basically the reason why these are listed in this order, and I have them specifically numbered as 1, 2, 3, 4. So atom electronegativity and size, specifically when talking about iodine, size is the important factor, plays a role in how stable that conjugate base is or how acidic that original acid is. So our propane and the conjugate base of that, when we think about the atom electronegativity, that carbon atom is not very electronegative at all. The carbon atom is remarkably small, especially in comparison with an atom like iodide. There is zero resonance potential on this, so this lone pair of electrons has nowhere to move on this compound. There are no electron inductive effects. There are no electron withdrawing groups on these carbons pulling electron density and stabilizing that negative charge. And the orbital where those electrons go are in an sp3 orbital. So that means those electrons are not being held very tight to the atomic nucleus, meaning that those electrons are relatively far from those protons, not allowing any sort of stabilization of our conjugate base. All right, let's move on and look at the Pka table in more detail. So in the first slide, I showed the example of hydroiodic acid. That is the most acidic compound, and propane, which has a pK value of greater than 60, and that is the least acidic proton. So all these other compounds fall somewhere in between. And so again, as you're looking at this, think about formation of the conjugate base for each of these. So I'm going to draw in a couple of these. So if this hydroiodic acid reacts with a base, we're going to form the conjugate base of the iodide anion. If the protonated version of acetone reacts with a base, we're going to form acetone. For hydrochloric acid, we would form the chloride anion. This is a protonated carboxylic acid. So carboxylic acid is protonated one more time on top of this acidic proton. So for the deprotonated version, we actually have simply carboxylic acid. This is the protonated version of ethanol. Once you deprotonate this, you form ethanol. The pKa value for the protonated version of ethanol is negative 2.4, where if we look over here, we actually have ethanol, and the pKa value of ethanol is 16. So there's a much lower pKa value if we're looking at the protonated version of ethanol versus ethanol in its original form. So this proton is much easier to donate than this proton. Once this is deprotonated, we get the carboxylate anion. So this is very stable for a couple reasons. So even though there's a negative charge on it, it actually is distributed between two oxygen atoms via resonance. We'll talk about that a little bit more later. And then we also have the strong inductive pull of the fluorines attached to this carbon. Hydrofluoric acid is the least acidic of the halogen row on the periodic table. So hydroiodic acid is the most, and then hydrobromic acid, which I have included on this table, and then hydrochloric acid, and then finally hydrofluoric acid. So even though the fluoride is the most electronegative atom, it's also the smallest atom. So size, in this case, plays a larger role than electronegativity